The James Webb Space Telescope is due to launch early in the next decade. This mission will look back to the very furthest reaches of space to see galaxies that have a redshift of 15 or more, where the visible ultraviolet light they emitted has now shifted to near and mid-infrared wavelengths. Sometimes known as successor to Hubble, there are many aspects of James Webb's telescope that are very different, such as the wavelengths of the light it will detect, its orbit, and its size. All objects, including telescopes, emit infrared light, which makes the faint infrared light from the distant early universe difficult to detect. This light could easily be swamped by brighter and closer infrared sources, such as the Sun, Earth, and Moon. Therefore, the James Webb Space Telescope's 4 scientific instruments will be protected from these objects by a tennis court-sized sunshade, as well as being placed at the second Lagrange point L2, an orbit where the Sun, Earth, and Moon will be in the same direction at all times. When it's launched, the James Webb Space Telescope will be the largest space telescope ever flown, with a primary mirror that is 6.5 meters in diameter. In fact, this space telescope mirror is the first to have a diameter that is larger than that of the launcher fairing, and it will have to be folded to fit into the ESA Ariane 5 ECA launcher. Designing and building a mirror of the scale that will unfold is one of the major technological developments of this mission, and has never been achieved in space before. During its journey of 1.5 million kilometers to L2, the James Webb Space Telescope will be fully deployed. Once the communication antenna and solar arrays have unfolded, the giant sun shield will open out, exposing the folded mirror. The sun shield is made of a polymer-based film and will have to be covered for the launch. Designed to block out sunlight and to keep the entire telescope operating at 33 Kelvin, the sun shield is multi-layered. Once it has been fully opened, it will then separate into 5 layers. The large primary mirror is made up of 18 hexagonal segments that will also unfold and move into position en route to L2. The James Webb Space Telescope mirror is designed to resolve the faintest detail possible for its size when observing near-infrared wavelength. The hexagonal segments of the mirror will be movable to allow for fine-tuning of the images in orbit. With this huge mirror and cold instruments, the James Webb Space Telescope will be equipped to detect highly redshifted light emitted from the earliest galaxies.
Hubble provided a glimpse into the distant past that has driven the development of James Webb. This new space telescope will provide a better view of the very distant galaxies revealed by Hubble.
The James Webb Space Telescope will detect the redshifted light from the very first stars that formed. When these formed, they ended the cosmic dark ages. This period followed the emission of the first light after the Big Bang, which is now detected as the cosmic microwave background. Little is known about the nature of these first stars, or exactly when they were formed. This mission will also conduct ultra-deep infrared surveys of the universe in search of the very first galaxies. This will help astronomers to tackle some of the fundamental questions about galaxy evolution, such as, how did the first galaxies form? How did we end up with the large variety of galaxies we see today? And what is the nature of the relationship between the large black holes at the centers of many galaxies and the galaxy that hosts them? The processes by which stars and planets are made are also poorly understood. Using the near-infrared portion of the spectrum, the James Webb Space Telescope will be able to infiltrate the dusty shrouds around newly born stars to study the young stars themselves. This telescope will also allow astronomers to investigate systems of planets orbiting other stars, watch how they form, and find out what organic molecules they contain. This along with studies of the cold, icy bodies in the far reaches of our solar system, will help trace the origins of Earth and life in the universe.
In the tradition of the Hubble Space Telescope, astronomers will use its successor, the James Webb Space Telescope, to follow the redshift back to the earliest stars and galaxies. By constantly pushing technology to its limit, they are sure to achieve their goals. I'm Rebecca Barnes. Thank you for watching the Science at ESA vodcast.